All right, guys, we're getting into the second part of the waves unit. So we finished waves and we talked about sound a little bit. Now we're going to start talking about light. So let me get into sharing my screen. And let's open up this PowerPoint here. So we're talking about electromagnetic radiation. That's the fancy word for light. So electromagnetic radiation. Let's first just do a little bit of review on waves. So first of all, remember most waves are either longitudinal or transverse. Longitudinal waves are the ones that are sound. So sound travels as longitudinal. They have the rarefactions and the compressions. And then, but light or electromagnetic waves are transverse. So that's where the action of the wave is perpendicular to the motion of the wave. So we'll take a look at those and we'll try to review that. There's a transverse wave here. So let's try to remember a few things. First of all, we look up here. What is this this box up here? This distance from crest to crest, or we could measure it from trough to trough, or any one same spot. Remember that's amplitude or wavelength. Sorry. And then as we go, this one here, the distance as we go up or down into the troughs or up into the crests, that distance from this normal position. This one here, that one is the amplitude. Okay, so just a quick review there. Now let's get into light. Here's a quick video, and I know you love it when I do this. So watch this video.
Professor Dave, let's learn about light. He knows a lot about the science stuff. Professor Dave explains. Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me.
All right, so back from the light video. All right, so let's first just talk about this electromagnetic radiation spectrum. So what we have here is the same chart that they showed in the video. These are the types of radiation or the types of light. What we have up here is the wavelength. All right, so wavelength like here, and then remember frequency is the number of waves per unit of time. So what does this picture show about the relationship between frequency and wavelength? Is the word that's blocked out. You can't see it down here, but notice that as the wavelength gets shorter, the frequency increases. Okay, so we have kind of low level radiation down here, and we have high frequency radiation up at the top. And we'll look at how those change as we go through the spectrum. So here's a quick overview of the spectrum. First of all, there's radio waves. Radio waves are the lowest energy on the electromagnetic spectrum. Radio waves include just what you listen to on your radio and TV signals, satellite signals, things like that. What we use to communicate with boats on the sea, that kind of stuff is all radio waves. Okay, next. We talk about electromagnetic waves being produced electrically by charged particles. They can travel in a vacuum because they don't need a medium to go through, and they travel at the speed of light. They're also known as electromagnetic waves. So here's a few more, a little bit on that too. There's that spectrum again. All right, so first of all, radio waves are the longest wavelength of the electromagnetic spectrum. We use them for TV broadcasting, AM, FM radio broadcasting, heart rate monitors, cell phone communication, MRIs. Is a picture of an MRI here. Okay, next one is microwaves. Microwaves is we're moving up the spectrum. This is a shorter wavelength, higher frequency wave. It is included in microwave ovens, Bluetooth headsets, broadband wireless internet, radar, GPS. Okay, next one is infrared radiation. So we're getting closer to the spectrum that you can see. We can't see infrared, but we're real close. Infrared wavelengths between the microwaves and the visible light are the infrared ones. So microwave is here, we'd have infrared, and then the light that you can see. So night vision goggles, remote controls, heat-seeking missiles all use infrared. Infrared is also heat, so you feel this. You can't see it, but you can feel it as heat. Visible light is the visible spectrum. Okay, it's the one that we can see with our eyes. Violet is the highest frequency. Red is the lowest frequency. Maybe you remember from your middle school, maybe you use Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Well, ultraviolet's out here where you can't see that. Okay, ultraviolet's the next one. These are shorter wavelengths, higher frequency. We use it for black lights, security images on money and things like that. Harmful, this is harmful, so we can use it to sterilize our medical equipment. It's what causes sunburn. Remember, you notice that your sunscreen is for UVA and UVB. It's talking about different types of ultraviolet light. And exposure can cause skin cancer. All right, X-rays are next. X-rays are tiny wavelengths, high frequency waves. They are used for medical imaging, airport security. All right, and it doesn't take a whole lot to be damaged. That's why when you get an X-ray, coat on just to get your teeth, not everything else. Then there's gamma, shortest, smallest wavelengths, highest energy electromagnetic waves. Sterilizes medical equipment, cancer treatment to kill cancer cells, but it's also very dangerous because it can kill all living cells. All right, so that's our frequency. You're going to be responsible for an electromagnetic part of the spectrum, so we're going to give you an assignment to do right there, but that's our end of our notes for today. So hope you had a good day. We'll see you later.